Okay, good morning, everyone. Let's get started. My name is John Kaz. I'm with the HPC group, and I'll be teaching this morning in the introduction to Manycore. And this afternoon, my colleague Todd Evans will be teaching in the more advanced Manycore session. And at any time during this presentation, if you have a question, please just raise your hand and ask. You don't have to wait until the end of a slide or the end of a session. And if there are any questions online, I'll just ask Virginia or whoever is monitoring the online questions to ask me, and I'll repeat them for everyone and try to answer. Okay, so let's get started. And that's the URL where you can download the slides. The version I have is slightly different. I'll point out the difference when I get to it, but there's only one tiny difference. But you can go there now and download the slides if you want and follow along on your laptop, or skip ahead if you get bored. And before I start, I want to give a little background to this training and this whole Manycore concept. This is training that has grown out of 4 years of training to support users on Xeon Phi processors from Intel. The first generation was KNC, which is in our current version of Stampede, and the next generation is KNL, which you'll be running on later today. And what we've tried to do is broaden the training a little bit, because in the future going forward, we see all processors as becoming Manycore. And that's what this first session is about. And so what do we mean by Manycore? You might hear us or other people talk about multi-core or mini-core, and there is no hard and fast definition. And what we refer to when we say mini-core is sort of an order of magnitude increase in the number of cores on a chip. Where before you had 2, 4, 8, maybe 12. Now, today you're going to run an architecture that has 68 cores on a single chip. So this change in architecture, this difference in scaling, changes how you have to program for it. And so you might have to learn new concepts or reinforce areas of your code that you haven't paid attention to before. And we'll get into all of this. And so first, just a little bit of a concept of a core. So when I speak today, you will hear me say CPU or processor. And when I say CPU or processor, I'm talking about sort of the physical object, the chip. When I say core, I'm referring to sort of the execution unit, where you do a floating point operation or an integer operation, or you load or store data to memory. That's what I mean by a core. It's sort of a single physical object. Now, it gets a little more confusing because cores can run more than one thread of execution, which I'll get to in a little bit, because of hyperthreading or hardware threads. But when I say a core, this is what I mean. Now, cores share resources, and that's where we get into trouble. If all of the cores on these chips all had their own independent resources, it would be pretty easy to scale up and increase performance. Okay, and so I'm going to just mention the concept of a cache. It'll come up later, but this is how we improve our access to memory. We use caches, and most of you are probably familiar with caches. It's basically a smaller, lower latency, high bandwidth memory that hides the latency to main memory. One of the issues with caches and main memory is now some of these resources are shared. L1 is almost never shared, but you'll see in the case today, L2 is actually shared on the chip we're going to talk about. And memory, of course, is shared among all the cores. And so since I have this shared resource, there has to be some energy, some power, some resources on the chip dedicated to keeping this all consistent.
CP stands for
clock. I was going to say clock cycle, but yeah, periods. But so 4 clocks to get to L1, 11 clocks to get to L2, and mini clocks to get to main memory. Okay, and so why do we need mini-core? Why are chips changing this way where we're just getting more and more cores on a chip? Well, increases in performance for processors are pretty much a result of the increase in the resolution that they can make these transistors. And so that's what Moore's law actually states, that the transistor density doubles every 2 years. It's not a statement about computer performance. It's a statement about, I guess, silicon and how they fab chips. Now, as a result of this, they can do many things. One of the main things they've been able to do as they've made these transistors smaller is increase the frequency at which they can run. And traditionally, that's where you've seen your performance gains. Another thing they can do, since they have more chip real estate, they have more transistors to play with, they can add functionality to these cores. They can make them, how can I say this, more adaptable. They can do things that we were doing in software and put them into hardware. And that's where you get the pipelining, out of order execution, cache prefetching, the SIMD units, which will be the vector units we'll talk about later, and bigger caches. And so what this has resulted in is a doubling of performance about every year and a half. Okay, so you're like, well, that's great. Why is it changing? Why do I have to change my code? In the past, say, 15 years, I just get a new computer and everything runs faster. And that's not happening anymore. Well, so what was happening is, as these features got smaller, they could go to lower voltages and take the same power and increase the frequency. And so as I increase the frequency, even if I have the same processor, if it's running twice as fast, if my problem is what we call compute bound, I should get an answer twice as fast. And so this was very easy for us in the scientific community, because I could just keep moving my same old code to new architectures or new processors, and it would get faster each time. And I didn't have to change much. Well, that's no longer true. Now we're having to worry about things like leakage current. And so we're losing more power to like a type of friction in the chip. Go ahead. Yeah, well, it's more, I think, leakage through capacitance. When the features get so small, there's an issue with capacitance and the features are close together. I don't know the exact details, but so you're not as efficient, right? You're having to pump more power, even though you're going at a lower voltage, to run on the chip. So it's less efficient. So this is one of the reasons why, rather than trying to lower voltage and make things faster, that we're making more cores.
You can almost think of it like the transistors are getting so small that now there's quantum effects that are occurring where electrons are going from one side of the transistor to the other, even though they're not supposed to be. And that's just constantly going on in the background. And that leakage term is becoming comparable to the term that we want, which is driven by the frequency. And so now we can't really make that leakage term any smaller anymore.
So we're hitting a physics limit with the technology we currently have. Yes?
Why doesn't that leakage current just make it not work?
I don't think it's large enough to, I mean, we're not losing enough power to stop it from working. So, okay, so I should repeat the question. The question was, why does that leakage term stop the processor from working? It's not, I don't think it's on the order of the power term. Okay, I have to use the mouse. The dynamic power, the change in voltage, the turning on and off of the switches. But not yet. But as we go to smaller and smaller features, it becomes more and more of a problem.
Yeah, eventually it won't work because of that.
Another problem is heat. So the more densely we pack this stuff, the more concentrated is the power, and it's hard to get the heat out. And also, the heat changes the characteristics of the circuits. And so this is why cooling is so important. And I'd say back in the day, I'm not sure anybody does this anymore, they cooled processors with like liquid nitrogen. And there's still a lot of liquid cooling because it's so efficient at getting the heat out of the processor. And so what's been happening for the past almost 10 years now is instead of making these every new processor with the same number of cores, faster cores, the chip developers have decided to make more cores, to use this silicon real estate to add more cores with the idea of, okay, I'm still adding performance to this chip, but instead of scaling up through frequency, I'm scaling out. Now, that's sort of a decision they had to make, but the impact on us is that now we have to program for it. We have to figure out how to use these resources that have changed in a different way. And we have to change our codes to account for this. And another side effect of this is they look at their power envelope and they look at their silicon real estate and they look at, okay, so how many cores can I put here? And they might say, oh, like on the chip we're looking at, I can put 68 cores here, but I have to run them at a lower clock frequency. So they're running, the cores on the chip we're going to talk about today are running at 1.4 gigahertz, not 2.7 or 3 or 4. And so this has impact on how your code runs, right? So now you've got many cores on a chip, but they're still connected to memory in roughly the same way. There may be more channels, but it's connected in roughly the same way. So all of these cores are sharing resources. They have their own resources. They have their own L1 cache. They have their own instruction cache. But maybe they share L2 cache or they share L3 cache. And they share the pipelines to memory. And so now other problems appear. A lot of times we talk in HPC about floating point operations and floating point performance. And since chips have increased in floating point performance so quickly, sometimes we'll say flops are free. Because for most codes, the limiting factor isn't the speed of the processor, it's how quickly you can feed the data to the floating point units. And now this problem is exacerbated when I add more cores to try to feed more data to these cores with the same pipeline or slowly increasing pipeline. And again, remember I mentioned cache. Now, what we're used to on the processors that we run on is that they're what's called cache coherent. So if core 0 changes a piece of data, core 2 will get the most recent version of that data. Now, this means core 2 has to know that core 0 changed its data, and maybe it's sitting in core 0's cache. So if core 2 goes to main memory to get data, it has to know that's not the most recent data, and it has to wait until core 0 writes that data back to main memory so core 2 can get it. So this takes up some extra hardware on the chips and makes it more difficult. I'd say it makes it more difficult for the chip developers to keep everything coherent as they go from 1 core to 2 cores to 64 cores. There's a lot more, you can think of it as juggling. There's a lot more balls in the air to keep track of. And so the memory bandwidth, I think I just mentioned that in the previous slide. So they're all sharing the same memory bandwidth pipes. So the memory bandwidth per core is reduced. There's contention. And now I talked about these cores are running slower because they want to put more cores on the chip, so their frequency is less. So if you have a program that only runs on 1 core, it's a serial program, there's a good chance on the newer chips it's actually going to run slower. Yeah. And that's not what a lot of people expected. And when we first put in Stampede, our current system that has the first generation Xeon Phi, many people, the first time they ran on the Xeon Phi, they were disappointed in their performance because it did not parallelize well, and those cores run very slow. But if you look at the performance in a whole, in total, there's more performance available on these mini-core chips with the slower cores. There's more peak performance available and more performance per watt available, because that's also a major factor in the chips of the future. How well do we save energy? How well do we manage the energy budget we have? And so these chips do really well at providing performance for the power that they use. But the trade-off is you have to write your code to use these chips. You have to, or refactor, redesign how you execute your problem. It's kind of like trying to learn how to drive a Formula One car. It can be very complicated. But if your problem is amenable to the parallelization and you can make the changes, you can get quite good performance. Now, in some cases, you might have to re-examine the algorithms you're using and say, pick a slower algorithm just because it parallelizes. And then you win overall. And there have been many cases where we've seen codes where we change the code, we optimize it for this architecture, we run, and then we find out that things that are slow are things that we've never noticed before, because these were parts of the execution that were not optimized or not parallel. And so now the parts that we could parallelize have dropped so much in time, these other parts stand out, and then we have to go back and examine them. So this is just a graphic sort of showing the progression. The laptop you have there probably has 4 cores in it. If you have an i5 or an i7, it's probably got 4 cores. Most of the clusters you've run on recently are probably dual socket nodes. So there's 2 CPUs. Each one has 8 cores or 12 cores. Stampede, that's our current system that we're retiring right now. It is a dual socket system, 8 cores per chip, 16 cores total. And then it has its first generation Xeon Phi as an add-on card. So it's the Phi part's not a self-hosted node, which caused all sorts of problems, but that was sort of our first foray into Manycore. And so what we have now, what we've just installed, and we're still in early user period, we're about to open it up to all of our users, is Stampede 2, and that's composed of these KNL nodes. And in the second part of this discussion after the break, I'll go into detail about the architecture, the hardware. Okay, and so if you want to optimize your code for these systems, one of the best things you can do is try to simplify your code. Simplify your loops. Try not to do a lot of pointer chasing, a lot of small functions, or if you're using C++, many methods, simply because these techniques confuse the compiler and it doesn't understand what you're doing. If the compiler can understand what your code's doing, the optimizers are pretty good about putting in vector instructions and trying to prefetch data. If it can understand the pattern at which you're accessing data, it will try to prefetch cache lines so that data is there when you need it. If it understands how you're doing your operations in the same operations, it will use vector operations rather than just scalar operations. And you'll need that to get the performance of the floating point units. And the part about branches and conditionals is if you've got loops with if statements in the middle of the loop, when the optimizer works, it doesn't know which direction your code's going to go in. So it doesn't know which branch of the tree you're going to follow. In general, that means it just throws up its hands and goes, oh, okay, whatever. I'm not even going to try to analyze this or optimize it. And so there's some basic things you can do to your code to help the compiler. So you don't have to add directives and intrinsics and do a lot of work on your own to hand tune your code. But the last statement is, I guess, the biggest one. You've got to be able to run in parallel to use this architecture efficiently. And by parallel, I mean multi-threaded. For parallel nodes, multitasking, say with MPI. Multi-threading, you could use OpenMP or pthreads or other threading technologies if you have them. And also by parallel, I mean vectorization. Because the way the floating point units work, we'll get into this in a little bit, you're doing multiple floating point operations in a single clock. So that's parallel performance too. So here are the different levels. Sort of at the largest, it's multi-node. You run on several nodes, which in our world generally means you're using MPI. At the next level, there's multiple sockets. Now, in general, on the KNL nodes we're going to run on, it's a single socket, but on most of the clusters you run on, it's probably two. And this is pretty much transparent to the user. When you run your code, you don't have to say, I'm running on socket 0, I'm running on socket 1. Your processes run wherever the scheduler, the Linux scheduler, puts them, and they can access memory, and everything is coherent across those two sockets. But you should realize that you can take a performance hit by running on one socket, but accessing memory through the other one. We have a question. A user would like to know what's pointer chasing. So pointer chasing would be, an example would be, let's say I have a linked list. And if you know what a linked list is, that's basically a way to jump around in a collection of data non-sequentially or without some sort of fixed stride. So what happens if you're following data through pointers, pointer to pointer to pointer, the prefetcher cannot figure out how you're bringing data into the cache. And so it cannot figure out which piece of data you need next. And so what'll happen is a lot of your data loads will be cache misses. And when you get a cache miss at one level, it goes to the next level of cache. You get a cache miss there, it goes to the next level of cache. And if this pointer chasing is over a large memory area range, you will go all the way out to main memory for each hop. If you can think of it as like a hop from one data element to another for what you need to load. Is that answering? Okay, so I'll go on. And so then the next level or the next hierarchy we have of this parallelism is multiple cores per processor or CPU. And so where does your process run? Where does your thread of execution run on these cores? And in general, okay, so we run the Linux operating system. I'd say most HPC clusters are running Linux, maybe not all. And it schedules these processes of execution with its own schedule. We'll get into this in a little bit. But it's possible they can float from core to core. And so how your processes are spread out across these cores may not be optimal if it's completely left up to the operating system. And sort of the next level of parallelism, which I haven't really discussed up until now, I mentioned it, it's what we call hardware threads or hyperthreading. Intel calls it hyperthreading on your laptop. They'll call it hardware threads on the KNL. I'm not sure what the major difference is other than on the KNL you can have 4 hardware threads, but on your laptop you can have 2 hyperthreads. And what this means is you can run 4 processes at the same time on one physical core, sort of. What it is, they're actually sharing execution units. So one process might be loading data. One process might be performing a floating point operation using the data stored in the current registers. Another process might be storing data back to memory. Another process might just be decoding the instruction or setting up the pipeline. So these 4 different processes can do something on this physical core in one clock, but they're using different resources of the core. Now, I have to say, in practice, I think I've only seen one case where running 2 hardware threads on one physical core showed an improvement in performance. And the improvement was just on the order of 1 or 2%. So in general, I don't recommend running this way, but I do recommend trying it because it's fairly easy to do. Because what you're doing is you're just running more threads of execution than there are cores. And if you do your placement right, it may give you an advantage. If you have a code that has a lot of stalls, so let's say you are pointer chasing, and so most of the time your process is waiting for something to be loaded. And it's only going to be a single cache line because it can't prefetch. This might help you. So if you have 4 processes waiting, maybe one of them will have some data so it can do some useful work. I'm just saying, in my experience with the HPC codes I've worked with, I haven't found it to be that helpful. So this is just a graphic of what I just talked about, the different hierarchies. And so another thing that makes this difficult, at least in my mind, is I have all these levels of hierarchy, and how I handle them is different for each level. So at the top level, I'm probably using MPI to communicate between nodes. Sort of at the core level, I'm using MPI and some sort of multi-threading tool. Sort of at the socket core hyperthread level, I may have external tools like NUMA control or libraries within my code to specifically assign my threads of execution to a specific core or specific hardware thread. And what I don't even mention here, which I'll get into a little bit, there's also vectorization, which shows up as a floating point unit on the core. That's another type of parallelism you have to optimize for. So this is a picture from a tool that looks like it was written in 1989, where they could really draw rectangles very cleanly, rectangles and straight lines. And this shows the processor layout of, I think, one of our systems. It's not Stampede, but you can clearly see there are, I'm going to use the mouse, 8 cores here, 8 cores here, and these different NUMA nodes, it's different sockets. The whole system has 64 gig. And then you can sort of see the bus connections on the side. And I think LS Topo is installed on all of our systems. So if you log in, you can just run LS Topo. If you have an X11 connection, right, this GUI thing will pop up and you can see it. And it's kind of nice. It gives you a very quick picture of the hardware if you're interested in the nitty-gritty details.
So this is obsolete, or is it
I'm not saying the tool's obsolete. I'm saying the graphics are. No, well, so this chip is old. This chip is probably, did you do this on Maverick? It's got 64 gigs, so it's not Stampede. So this is probably a 4-year-old system because these are 2 8-core chips. I think the next slide is the KNL. So here's what it looks like on the KNL. So when you say obsolete, I assume you're referring to the architecture, not the tool. Yeah. Okay, so this is a KNL. As you can see, it's a lot busier. Now, there's only one socket here. So there's one grouping of cores, but notice that this is L2, this is L1. So now there's a shared L2 between these two cores. Now what this doesn't show you, and I'll get into later when we talk about the architecture, is how these cores are connected. Because before, on the previous Xeons, the cores are pretty much connected in a ring, a simple ring. On the more recent Xeons, if you look at it, it's kind of strange. It's like two rings. It's like a figure 8 maybe. And that's how they sort of pass data among themselves between caches. Now, the KNL is connected in a mesh. Sorry, is there a question? Okay, so you hear me, I'll say thread of execution. I'll probably still say thread of execution. Todd's term is more task of execution, or tasks or units of execution. And in the Linux OS system world, you have processes. A process you can think of as a unit of work. That's what actually runs on the core, and it gets scheduled by the OS. So if you know what MPI is, you can think of MPI as just multiple processes that communicate with each other. Now, we also talk about what we call multi-threaded parallelism. What that means is a process can spawn what we call threads. Now, at their base, a thread is a process, but multiple threads have a shared memory space. So you can, I think of the process as like the parent and the thread is like the children. Because even though they can all use these execution units, they can access the same memory, which is a good thing and a bad thing. The good thing is it's less overhead and it's easy to use multi-threaded programming. The bad thing is it's very easy to get in trouble. And when you make mistakes, they're very subtle and hard to debug. But both of these techniques of parallel, or of programming and processing, are in parallel. And this is what you need to use to program these multi-core or mini-core systems. And when you think about this, you're going to be on an architecture that has 68 cores. And so on these 68 cores, you may be running 68 processes. You may be running one process that has 68 threads. So it's still 68 tasks of execution running across these cores, but they're managed and synchronized in different ways. And that's where you get into MPI and OpenMP. And it's also where you have to begin to think a little bit about affinity. Because if you take the example of a node with 2 sockets, what we've found is codes that can do, say, MPI and OpenMP well, a lot of times it's best to run one task per socket, and then the number of threads equal to the number of cores. And so the processor is set up to make the cores really tightly bound and cache coherent among the cores on that processor. That's in the hardware. Is there a question?
Yeah.
Sorry.
Is vector length tied to number of hardware threads per core, or is it independent?
Vector length is independent of number of hardware threads per core. They're getting ahead, but okay, I lost my train of thought. Sorry. So if you have a process with multiple threads, you want the threads to be as close as possible in the memory hierarchy, right? So if thread 0 needs to share data with thread 1, maybe they can share it through the L2 cache. You don't have to go to main memory. Where if they were actually running on separate sockets, the only way they can talk is through main memory or through the bus between the sockets. But it's a higher latency and it's lower bandwidth. And so you have to be concerned about where all of this falls. Now, the good thing is the tools we use on the KNL right now, by default, are pretty good about assigning the cores to the process. Now, within this process space, how the threads are assigned, that might be a little bit different. And we'll get into that later and talk about how to change how your threads are assigned to these cores. Okay, and so I talked about parallel, and here's just how the many ways you can run in parallel. And we have some people where the first way, that's all they need. We even have a tool for it called Launcher that lets you run embarrassingly parallel problems so that each run is completely independent. It's working on independent data, it's providing independent outputs. And we just have to ensure that when this runs, it's assigned to the correct cores. Fork, I don't think I've run into anybody using a program that does a lot of forks in the past 10 years. Almost everybody we deal with, our users, they're running MPI codes or MPI plus OpenMP codes, a few pure OpenMP codes, and every once in a while, someone's using pthreads. Those are the primary means of parallelization on our systems. And that's what I and most of the people in the HPC group I work with have experience in. Yes?
Don't do two, or at least some of those just do a fork will, like an executive and others.
Like I say, I haven't run into a code that does that in quite a while. Oh, sorry. The question was, are there some codes that just do a fork to start multiple processes? They can do that, but I haven't run into a science code that does that in probably 10 years. But it's still allowed. I mean, it's a Linux operating system. It might. I don't know if it's using an actual fork mechanism to spin up other threads or the OpenMP. It is?
I think it does, yeah.
Pthreads will do a fork, I think.
Okay.
That's actually basically OpenMP has that covered, so it happens there.
But you're not, okay, then I guess what I'm saying is you're not putting it in your code, right? Okay. So that's what I haven't seen. I have 10 years ago, I did see someone who that's how they ran their code. They basically saw how many cores were there and they forked off that many processes and yeah. Okay, any other questions? Okay, so scheduling. Linux has a scheduler. And so Linux runs many processes, not just yours. So there are system processes that have to be run. There are housekeeping utilities it has to take care of. And so when you run on a Linux system, let's say you just run an OpenMP code, so it's just multi-threaded. What I've noticed on some of our systems, if you don't provide any other guidance that on our current system, Stampede, I'll see threads running on 14 out of 16 cores. I'll see 2 cores idle, even though I'm running 16 threads of execution. I'll see the same thing sometimes, not as often with MPI, say where I'm running 16 MPI processes, that 1 or 2 cores might just sit idle. And it's like, I thought the scheduler's #1 goal was to use idle cores, but not always. It's not perfect. So what Linux uses to make these choices is kind of a black box for us. I assume there's some tunables, but in general, we don't touch it that way. And I can't always predict what Linux is going to do because I have seen it start tasks in one place and then move them to another socket, which has issues for memory access. And so what it's trying to do is balance this load, but it's not clear that it's always using CPU idle time per core or if it's using memory hierarchy, although it's sort of supposed to. But then The operating system has a very different job than what your application does. The operating system is set up to support maybe multiple users and many different activities at once. So it's more worried about performing efficiently and, say, time slicing the processing. What's different is that when you run on an HPC cluster, in general, you are usually the only person on that node. It's just your job. So you really don't care about things the OS has to handle multiple users or multiple accesses. You just want it to run your job fast. So some of the default settings and some of the things Linux is designed to handle get in your way a little bit. And so what I'm going to highlight here, the main thing I want to highlight here is this first touch policy. If you run a multi-threaded code, there's something called first touch. Basically, the first task of execution that allocates memory does it through, say, a socket, through a certain memory pathway, and the processor remembers that. So then, if you then run multiple threads to access this shared memory, the threads that run on the different socket, they will access that memory through the other socket, because that's where the memory was allocated. And if the process that allocated happens to get moved by the scheduler to the other socket, it will still try to access that memory through the socket 0. So say it's on socket 0 and moves to socket 1, it will send its request through socket 0. So the memory will get to that process in a roundabout way. It will not go straight to the process. So this can be an issue, especially if you have a dual socket system. And this comes up when you're doing multi-threaded programming. One of the things I like to do in multi-threaded programming is turn everything into a subroutine or a function, put the guts of my operations in the function, and basically pass data into private variables. Then I know whatever data I'm accessing was allocated by the thread I'm running. And then I also make sure that these threads can't move. And that minimizes this problem. But it's something you have to be aware of, because we get people all the time. Hey, I ran one day and I got this performance, and I ran the next day and I got this performance. It's like, well, you're not pinning anything. You're not setting any affinity for the threads that you're running. And if I go look, I can see that it's floating around, or it might not be running optimally. So this is something you have to worry about for performance and consistency. Now, the good thing is, like I said, with the tools we use, especially with Intel MPI, if you're running an MPI OpenMP program, it's pretty good about setting up sort of a walled garden for your threads to run in, where they shouldn't float across sockets or across cores. And so this is what we mean by load balancing for data locality. So if I have, let's say in this case, I'm running 8 threads, and the threads sometimes share data with their neighbor. So their neighbor 0's neighbor is 1, one's neighbor is 0 and 2. Ideally, you want these threads as close as possible in the memory hierarchy. So maybe they only have to go one level up in cache to find the data they need. So in this case, if, let's say, 0 was actually sharing a lot of data with thread 4, then for it to share data, it's got to go all the way. Well, in this case, with an interconnect, it's got to use MPI. But if it's on a NUMA node, it's got to go to main memory. Or it's got to go to the other NUMA node, it's got to go to main memory. And so that means there's a delay. There's less bandwidth, and there's higher latency to access that data. And so ideally, we just try to sidestep all of this. So we use tools like NUMA control, which basically allows you to pin a process to a core or a range of cores, or to set memory affinity to what's called a NUMA node. Now, NUMA stands for non-uniform memory access. And so in general, before the KNL, a NUMA node was pretty much sockets. So if you had 2 sockets, you had 2 NUMA nodes. And so you had memory attached to each socket. So if I go back up here, this LS topo diagram, you can see the total memory is 64 gigabytes, but there's 32 gigabytes here that's aligned with this socket, and there's another 32 down here. Now, this doesn't mean this socket can't access all 64 gigabytes. It just means this is the NUMA node that's related to these processors. So that's the quickest access.
So it's a NUMA node, a physical thing, or is it something with OS?
A NUMA node, okay, so the question was, is a NUMA node a physical thing, or is it something to do with the OS? It's a representation of the OS. It's a representation of the hardware that the OS is trying to reflect. So the NUMA node concept is, well, it's in the hardware, but how it's represented is in the OS. And the reason I'm sort of saying it in this roundabout way is because later when we get to the KNL, I will show you multiple ways NUMA nodes can be configured. Like I said, before I started using Xeon Phis, I would think of a NUMA node as a socket, because in general, there was 1 NUMA node per socket. There's memory attached to the socket. What you will see is with the Xeon Phi architecture, there's another class of memory, this high-speed memory, that can be configured many different ways. And the way when it's configured a certain way, it's a separate NUMA node. That's why. So we'll get into that in a little bit. Okay, and so NUMA control just handles processes. It does not handle threads. I don't think I've ever used task set, but sched set affinity is a library you can call that uses the same libraries that NUMA control uses, where you can assign your current thread of execution to a core or set its memory affinity. And so sched set affinity is something you can do from within your program. And since it's from within your program, you can assign threads to different cores. Where with NUMA control, you're pretty much just building this range of cores you can run on, or a walled garden that process and any thread spawned or forked by it can only run within that range. That's what NUMA control does. OMP proc bind, GOMP affinity, which is the GNU tool, KNP affinity is the Intel tool. These environment variables are all set up to tell the runtime system how you want to distribute your threads over the range of cores you have allowed. And we'll get into this. And each MPI implementation has their own affinity tools, and Intel MPIs, which is the default on here, is pretty good. That's why I say a lot of this you don't have to worry about, because by default it usually does the right thing, the MPI version. Now remember, MPI is at the process level, not the thread level. So if you're running a hybrid code where you have tasks with threads, what MPI is going to do is give you a range of cores that process can run on. And it's up to you to set these other environment variables to make sure your threads are distributed correctly. Now, like I said, in general, if you're not using hyper-threading and you're not running on, say, a 2-socket or 4-socket system, the defaults on KNL are fine. And just a little nomenclature. When we talk about speed up, we're talking about the increase in performance due to parallelism. And it's simply the time it took to run on one core versus the time it took to run in parallel. And this could be parallel threads, parallel processes, completely separate processes, however you want to define it. And so efficiency is just, what was the cost of this parallelization? What was the overhead cost? And so if you have what we call linear scaling, this efficiency would be 1. Because every time you add a core, you basically increase your power. Go from 1 core to 2 cores, you're twice as fast. 1 core to 4 cores, you're 4 times as fast. In general, you don't see this a lot, especially not at really large scale, because a little bit of overhead cost. Granularity is the amount of work you assign to each task. So that's how much do you divide your problem up so that it can run in parallel. There'll be some examples where you might have made the wrong choice. And so we're going to talk a little bit about load balancing here and how you can handle load balancing in your code or your workflow. And so in this case, you have 10 pieces, you have 10 cores. If there's no overhead, it's simple. Because what you want to do is minimize your wall clock time. And for load balancing, what you're doing is trying to make sure that each task has the same amount of work. And you would be amazed at how often we look at codes that look like every task should be doing the same thing. And then you go into detailed profiling and you find they're not. And you have to dig deep to figure out, well, why are the tasks at the end finishing so much sooner than the other tasks? They all seem to be doing the same amount of work. Just as an anecdote, I once had an issue where all the tasks were reading in data, processing data, and this was on like 64 tasks, and they're all reading in the same amount of data and processing the same amount of data. But there was a huge amount of idle time on the early tasks, and the tasks at the end were busy. And so what I figured out was that they were reading in files, there were 1,000 files, but they were all of different sizes. And so what they had done is they looked at the file sizes and tried to give the same amount of I/O to each task. But each task had a different number of opens and closes. And so what happened was the open and close overhead from the tasks that were reading all the small files caused it to go so much slower. So all we did was change the file access pattern to a round robin pattern and sped the code up by 30%. But it was something I didn't expect, because when I looked, it looked like they were all doing the same amount of work, processing the same amount of data. And so this idea about granularity is just that if you're too granular in the amount of work you give the tasks, there could be large differences. If you cut the amount of work per task too small, let's say you're in some sort of time advancing program and you're time stepping, and you're only synchronizing, or you're synchronizing every time step, when maybe you don't have to synchronize, but every 10. Well, every time you communicate and try to bring everything together, that's overhead. Let's say you have another case where, like I was talking about, you're doing I/O operations, you're opening files, but the way you split the work up isn't equal, but it looks equal in the way that you had the serial program written. So you have a loop and you just take a loop over 100 iterations and split it into chunks of 10. But let's say each iteration takes a different amount of time. So you need to change the unit of work, because your ultimate goal is to decrease your wall clock time, get better performance, and use the resources you have. Okay, so here's a case you have this 10 iteration loop, but you only have, say, 9 cores. 9. And each iteration of this loop takes a whole day. So what happens is you get through 9 iterations in the first day. Then on the next day, 8 cores sit idle while 1 core finishes that last iteration. So what if I could change the granularity of this loop to 100 or 1,000? Then whatever imbalance I have relatively would be less and my efficiency would be higher. So here's another case where another iteration, 10 loop traverses, but to set it up, it takes a millisecond. But each iteration is so fast, it's only 0.1 milliseconds. So once you're set up, it does all 10 iterations in 0.1 milliseconds. But the overhead was so high, my total time is now 1.1 milliseconds, where if I just run it serially, it'd be 1 millisecond. And so what's really going on here is there's not enough parallel work to justify the parallelization, to justify the overhead. Okay, so now we're going to get into vectorization. And so if you think about what's going on in a processor, it has to load the data to 2 registers, perform an operation, store the results somewhere. Now, I want to say most scientific codes, not all scientific codes, a lot of things are done at large scale where it is what's called SIMD, single instruction, multiple data. I'm doing the same thing on lots of data. And so if I don't have to decode a lot of different instructions, I can just decode one instruction and perform these operations on blocks of data. And that's what these floating point units have moved to. Vector units, which we had with the Crays and Fujitsus and NECs years ago. And they've turned their floating point units into vector units. So they can process many floating point words in one clock operation. This is another reason why it's important to worry about data access patterns, because there aren't just vector adds, there are vector loads and vector stores. In other words, there are optimized ways to move chunks of data in and out of the processor and to perform operations on them. And that's one of the strengths of the architecture we're going to talk about today. It has what we call deeper vector units. So it can handle more words in one clock. This is just a bit of the history. And so what we have here is, let's see, can you see the, okay, so SP is single precision, DP is double precision. And so this is the width of the vector unit. So 128 bits. So for SSE2, 128 bits is 4 single precision floating point. So 4 words. If you're running in double precision, 2 words. So it can operate on 2 words at the same time, or it can do 2 floating point operations on double precision in the same clock. And as we've advanced with Sandy Bridge, which is what our current architecture is, Stampede, the one that's being retired, it could do 256-bit. So now just double everything, right? 4 double precision, 8 single precision words can be operated. It's still 1 vector unit. With AVX2, I think they add the fused multiply add. So if what you're doing allows it, it can do a multiply and an addition in the same clock. FMA. And now with the Xeon Phi architecture, we have 512 bits. So now we're up to 16 double precision words. With the first generation of Xeon Phi, there was one vector unit. On the KNLs we're going to talk about today, each core has 2 vector units. So that's why it's so potent when you talk about peak floating point performance, because of these vector units. But you have to be able to use them, right? You've got to be able to feed it in these chunks of data. And that's what this Mike AVX 512 is. The previous generation of Xeon Phi, it was just Mike. And then with the new architectures that Intel's coming out with, Skylake, there'll be a Core AVX 512. It will also have these vector units. And so this is just a look at the sizes. And so here at the bottom, that's where we are now. Now, what you also have to realize is that, so every clock, I can do all these operations. But if my code's not vectorizing, then maybe I'm doing only one. And so then if I look at the potential performance, I'm doing 1/8 of what I could do, right? And so you have to be concerned about this at the lowest level. This is just an illustration of what it's doing. So if all your data is stride 1, it can load a cache line directly into vector registers. It's got special registers for the vector. And load both sets of registers, do the operation, do an update. And so you can sort of think of it, it's unrolling this very simple loop. That's what the processor is doing. If this were the operation, this is what it's doing with this vector operation.
So
Yeah. Yes.
this is important to have just one result from the operation on the paragraph.
Okay, the question was, is it important to have one result from the operation on the entire vector?
Like you're adding all of them together.
No. So what we're doing when we do this is we're doing these operations in parallel. So really I have 4 results here from 4 operations. So the vector operation, the chip assembler command, whatever, basically cause the vector unit to perform all 4 of these operations in one clock. And then there was a vector store. So there are actually 4 results stored. So it's not like I'm summing up everything into one number. I'm performing 4 independent floating point operations, but they're the same floating point operation.
So if I was summing up, I'd only get one.
Right. So that's a collective operation. And well, and so, yeah, that's not completely vectorized. I have to think of a binary tree whittling down, but this is like, I'm doing embarrassingly parallel, well, by a factor of 4 or 8, floating point operations. Okay, have another.
If we use OpenMP, so vectorization can be done automatically for.
So
Do we still need?
think of vectorization as like the lowest level of parallelization. OpenMP is above that because multiple threads should be running on separate physical cores, which means different vector units. But what this means is when you create an OpenMP section of a code, let's say you have a loop, you probably, if your iteration of the loop is only 8, you don't want to make that OpenMP, because you'd like that iteration count of 8 to be vectorized on one core rather than spread out those 8 iterations on 8 cores, of which there's only one floating point operation per core. Does that make sense? So you can think of vectorization as sort of the finest level of parallelization that will execute on these chips.
So is this done for us automatically?
Yes and no. In other words, the compiler, okay, the question was, is this vectorization done for us automatically? The compiler tries its best to vectorize what you've done. But as I was mentioning earlier, if you have simple loops like this, if you have an if statement in this loop, the compiler's not sure which branch it's going to go on or what it can load. If you had, say, a print in the middle of this loop, the compiler's going to, if the compiler can, it will take things, it will try to examine the data dependency, and it will move some things out of the loop. But sometimes it can, and sometimes it can't determine this. But there are ways to get around this. Later, we'll show you, you can put directives in that say, no, it's safe, vectorize this. And there are reports that the compiler gives you to tell you what it did and what it didn't do and why. And so you can go back and try to fix this. But by default, it will try to vectorize and optimize everything it compiles. Okay, I had another question. Yes, sir. Okay, so there was a question about if the memory should be aligned to improve the vectorization. And the answer is yes, if you can. It's nice if all of the arrays you're accessing are aligned the same way. Now, for the first generation of Xeon Phi, this was extremely important. For the KNL, it's not nearly as important. And it's something that's really hard to do. One of the things a lot of people do in computational science codes, especially finite difference codes, and to some extent finite volume codes, are stencil operations. Some of you may know what a stencil operation is. And in general, with a stencil operation, you have several arrays where you're accessing the I+1 component, the I-1 component, then the J+1 component, and the J-1 component. Now, unless you create copies of all these arrays you're using and align like the -1, the +1 copies of these arrays, it's hard to always guarantee alignment for your vector operations. So you're never going to get perfect alignment. But you can compile with a flag that tries to at least allocate the arrays on the same alignment. I think it's -align 64. We might have it mentioned. And this made a big difference on the first generation Xeon Phi. It does not make nearly as big a difference on the KNL. I'm not saying it's not noticeable, but it's not as hard. And when you look at this vec reports output, it will tell you maybe misaligned array, or it will create what are called peel loops and what's the other one? The pre-loop. It will change the way your loops are executed to try to keep the memory aligned and the vector units full. Okay? Okay, and so this is sort of what I was mentioning earlier. Let's say you have perfect vectorization. Everything is working great for you. You fill the vector units on every clock. And this is theoretically what this KNL could give you. One chip could give you 3 teraflops. Now, in reality, do we see that? No. Because this is assuming every clock will fill both vector units. Every floating point operation is a multiply add. And you always have data in your vector registers to fill the units. And so in general, this is unrealistic. So you're not going to get 3 teraflops. HPL, one of the benchmark codes used to sort of rank the supercomputers, it's pretty much, it's a high performance LinPack. It's basically a matrix multiply. I think it gets 65% of peak.
That's 2 teraflops, or maybe a little more.
Yeah, so maybe a little over 65%, because it's really hard to fill both these vector units. On previous processors or architectures, they could get up to 80 or 90% of peak, but they were shorter vector units, 1 vector unit. I'm just trying to set expectations here. And so this is sort of a little indication of the speed up you would get. So let's say your code is 90% vectorized. 90% of your code runs with full vectorization. And so if my vector width is 16, I'm getting a speed up of 6. Now, this is something that's very easy to test, because with the Intel compiler, I'm not sure if you can do this with GNUs, but you can compile with an option that says no vec. And no vec says no vectorization. There are no vector operations. And so a quick and easy way to see how well your code is vectorizing, compile it, just normal, optimization, 03, whatever, then do the same thing with no vec and compare the times. Because no vec will guarantee you're only using 1 floating point operation per clock. Okay, so what should you do? I already mentioned this several times, but the first thing is try to keep your code clean. Try to write it in such a way that you think if someone read it, the compiler, it can figure out what you're trying to do, how you're accessing memory, what floating point operations are you doing. Now, what this may mean is taking one loop and turning it into 6 different loops, right? To sort of simplify the operations within the loop. It may mean taking an if statement out and putting the loops in the if blocks if you can, or creating masks. So rather than have an if statement at every operation, you can create a mask. So if one of the ifs was, oh, if this, don't do anything or set it to 0, you can create a mask, so you just multiply the result by the mask. And that can be vectorized. So there are lots of ways to make your code amenable to vectorization. Another thing you can do, I mentioned earlier, you can put directives in there. And I prefer directives to intrinsics. What intrinsics are specific vector operations. The reason I don't like intrinsics is because every time a new processor comes out, these intrinsics change. And so they're newer vector operations for the new features of the processor. And so then you have to change your code. But with the directives, at least for Intel, I don't know about GNU, are fairly general in that they say, oh, you can vectorize this. This is not dependent on this. And so they will translate to compiler upgrades and architecture changes. If you want, you can actually tune assembly. And so Intel's MKL library, math kernel library, that's what they've done. They've basically taken a lot of libraries that computational scientists use and hand-tuned the assembly to run well. And that's why sort of this last point, if what you're doing can be done using one of these libraries, by all means do it. Don't reinvent the wheel, because companies and universities and people have spent a lot of time and money trying to optimize these libraries. And so these are the different levels of optimization for a specific architecture you can choose. Be very leery of Xhost. So Xhost basically just says, hey, compile at the highest level for the architecture I'm compiling on. And you have to be leery of that, because on the system you're going on to today, Stampede 2, the login node uses a Broadwell. That's an Intel processor. The compute nodes are all KNL, so it's a different architecture. So if you use Xhost on the login node, you're not compiling with the highest level of optimization that you can use on the compute nodes. So I'm just saying, if you use Xhost, be aware of where you're compiling and where you're running. What you can do, and this is what we do for a lot of the software packages we install, you can build what are called fat binaries. So you can compile it to be optimized for these AVX2 instructions and to have the AVX512 instructions. And so then you can run on this Broadwell and build and compile there optimally. But then when you run the same application or use the same library on the KNL, it will use a different set of instructions. It will detect what the processor you have is, and it will go down a different tree in the execution. And to be honest, if you're using a piece of software that uses configure, you pretty much have to do this. Because if you set your configure option, so the only optimization is AVX512, the first time configure tries to run a test, it'll fail because that processor does not support those vector operations. There's a question?
First question is, just previously you said to use -03 and the slide says -02, which do you recommend?
03. I think the point being made here is that if you use -02, it will use SSE2. It's a typo. So if you just do 02 with nothing else, it will use SSE2 optimizations. And I think if you do 03, SSE4, do you know, Todd?
I don't know.
Okay, so I'm not recommending you just, 02 is the safest, and I think if you don't use anything, I think it'll default to 02 if you don't put any 00 or anything. Was there another question? Okay. Okay. Loops. Pay attention to your loops. Pay attention to your loops sort of at the finest granularity for vectorization. The outermost loop, that's where you usually consider OpenMP, or you're looking at how you break things up to do domain decomposition or something. But sort of your innermost loop, that's where you need to worry about vectorization. So when you're looking at vectorization, sometimes you do a loop exchange where you might change the order of your loops because you want this loop to have enough iterations to vectorize. What this also means is you might have to change the way your data is laid out, because ideally on your innermost loop, you want it to be stride 1. So the compiler output, what we're referring to here is you can turn on lots of reporting through Intel compilers. So through our labs and at TAC in general, our default compiler is Intel. We found Intel to be the most performant compiler when compared to GNU and PGI, especially for Fortran. And Intel has lots of tools. You can turn on many levels of reporting. Like I said earlier, it will tell you exactly why it did not vectorize certain loops. And it will tell you when it did. And so if you look through this report, you might say, oh, that's my major loop and it didn't vectorize it. You read why, and you have to go back and look at your code and try to decide how you can change this. And then you can compile again, right, and see if it vectorized it. And again, every time you change something, and this has bit me more than I care to remember, test the performance. Make one change, test the performance. Don't make 2 changes and test the performance, because strange things can happen and you might think performance changed for the wrong reason. And so I don't think I can emphasize this enough. If whatever you're doing, you have a test harness or you have a nice quick test case, that's great, because you can rapidly test these changes. But please test every time you make a change. And don't forget to validate your results. I'd say it's much more uncommon now for me to see maybe incorrect results from a high level of optimization, but I have seen it. And so anytime you make these changes, do check your results. And as I was mentioning earlier, if you change loop orders, if you change the way your loops are structured, pay attention to how your data is structured. That may be a more important change. So you may need to change the order of the indices and how you access the data. Because ideally, you want stride 1. And you want stride 1 at the vectorization level. So you can fill these vector registers easily. They can come from single cache lines, maybe. And there are vector math libraries. I don't think they're ever automatically inserted. In other words, if I have a square root, I think the only way I get a vector square root is to actually make a vector square root call or a cosine or a tangent or any special math functions. But be aware that there are these functions and you can use them. But I'm pretty sure you will have to specifically put it in your code, that the compiler will not try to optimize your code by replacing a cosine with a vector cosine. And use the libraries whenever you can. We have a question?
First question, are there any math libraries that provide integration routines for Fortran?
I'm not sure what they mean by integration routines, just like integrate.
Second question is, what is stride 1?
Okay. So the first question was, are there any math libraries that perform integration routines for Fortran? And I'm not sure what they mean by integration in the most general sense or specific. The second question was, what do you mean by stride 1? I apologize. By stride 1, I mean when you're accessing data, stride 1 would mean that you're accessing words in a contiguous fashion. So if you have a vector, you'd like to access I, then I plus 1, then I plus 2, then I plus 3. That's stride 1, not I plus 10, I plus 20, I plus 30. If you have a 2D array, you want to access the data that's contiguous on the dimension. So I plus 1, I plus 2, not I, J plus 1. Well, depending on if it's Fortran or C, because the row major, column major order changes. And so you need to understand the programming language you're in and how it stores data, and try to, at the innermost loop, at the lowest level, access data in either stride 1 or the nearest fashion.
I'll talk about that in a second.
Okay.
The Fortran question is asking us for integrating functions. He is trying to respond to my mind.
Okay. I don't, so I'll just say I'm not aware of any special packages for integration unless there's something in MKL. In general, there are like sparse solver techniques where you can solve an integral problem, but I don't know of a general package. Oops.
Are the vector math calls vector cosine portable or different?
I am unsure of that. I bet they're not portable because I don't think it's part of any language standard. So I know they're in Intel. I don't know if they're in GNU. Some more tips for object-oriented code. Whatever you're doing object-oriented, put it as far out as you can. In other words, don't have loops calling methods, chasing pointers to different functions. And I'm not much of an object-oriented programmer. I started life as a Fortran programmer, and nice, big, beefy chunks of code is what the compiler can optimize. Lots of redirection through object-oriented methods. This is sort of like pointer chasing for functions, confuses the compiler. The compiler will try to inline small functions and then optimize that code. But if there are several levels of indirection, the compiler gives up. Say optimization flags. Please use your optimization flags. And if you have flags turned on for debugging, say floating point trapping, that actually traces back to where you had the problem, once your code is debugged, take that out. I had one case where I just told someone, hey, you don't need that anymore. Go 03 and take that out. Sped their code up by a factor of 2. So just be aware of which flags you're using, and when you're ready for production, compile with optimization. And yeah, I'm beating the drum here. Use math libraries wherever you can. If there are functions, if there are things you have to do that are already available in these libraries, try to use them. Don't reinvent the wheel, unless that's your purpose. I mean, maybe you can make it better. But most of the people we work with, they're scientists and engineers just trying to get research done. The computer is a tool. Their program is a tool. They want it to run well. They want it to run efficiently, but that's not their ultimate goal. I think we sort of already went over this, but 0, and 01, just quick and dirty. You want to see if something runs. 02, I'll do some basic optimizations, and if you don't do anything, that is the default. 03, that's what I recommend for the Intel compiler. I want to say, I think on GNU you can go to 04. I don't know. You don't know. These last two options, so pay attention. So IP is interprocedural optimization within a single file. So let's say you have a code or a subroutine or function, but there's lots of little functions it calls, but they're all in the same file because they all work together. So what IP will do is it'll try to inline all of those functions and optimize the code in that file as a whole. So it's a good thing. What IPO will do, and I rarely ever compile with this, is it will try to do the same thing across all your files, so your whole program. And the reason I rarely ever do this is I usually deal with codes that are tens of thousands of lines. I don't think I could get this to finish. There's too much there. And so the idea is if you have a large code and you're writing it, in your files, try to keep it sort of task-centric. It doesn't all have to be one routine or one function, but that file handles this task. And maybe it's easier to write sub-functions because you do things in different places. And what IP will do is try to inline those functions in the different places and make it as if it was one routine or one function with repeated bits of code. Because then once it sees that, it can optimize it because it can analyze the file as a whole. Now, if you don't have many files, say you only have 3 or 4, IPO is perfectly appropriate. And you can try it on a large one. I'm just saying, I haven't gotten it to finish on some of the larger codes I've tried to use it on, and so I usually don't bother. Oh, it's just saying what I just said. And this is an example of inlining. Basically, it's like it's just taking the code and sticking it in. Then it makes it one cohesive piece of code that it's easier for the compiler to analyze and optimize and see what the data dependencies are. And for you, it's easier to write it, with a function because you may call this function in several different places. And so for small functions, this is perfectly appropriate. For something really large, I don't know how inlining would work if the function it was trying to inline was large. Okay, and this is just, I was referring to these different instructions. These are the names of the processors they go with. So AVX, Sandy Bridge, that's what's on the current version of Stampede that we're retiring. Sort of the latest Intel iteration for HPC and servers in general is Haswell and Broadwell, and they support the AVX2 operations. And then what you're going to work on today is Knight's Landing, and that supports Mike AVX 512. Eventually, we'll also have Skylake processors, and they'll support something similar called Core AVX 512. And it's different because there's just a small subset of operations that don't overlap between the two. It's like, thank you, Intel. So now we have to compile for two different architectures on the same system. Okay, are there any questions? My throat's getting kind of dry. Go ahead.
Is most of this discussion really just pure design, or does some of this apply? Or you do that?
My background is scientific computing, but I would say a lot of this discussion applies to what the quants do in high frequency trading. Quants, I don't know what it's short for.
Quantitative analysts.
Quantitative analysts. So there are a lot of people from science and HPC in general who work in the financial industry for these high frequency trading companies, and they run on HPC clusters, although their problems are a bit different than ours. But they do use it.
Does it apply in like big data?
Big data is a loaded concept.
It's more Hadoop and like, has that much HPC.
So are we talking big data or are we talking high frequency trading? Yeah, so big data, I'd say, well, it's a nebulous concept and everybody defines it a different way. And the way that, say, Google defines it, it is a bit different in that it's not how quickly can I do these floating point operations, it's how quickly can I access this data spread out across many, many different servers and find the piece of data I'm looking for and maybe combine it with something else. It's a different problem, although they use resources similar to ours. Lots of computers, they want chips with really good memory access. They probably don't care anything about the floating point. And they also don't care as much about the interconnect because with their algorithms, there's not a lot of synchronization. And we need strong interconnects and huge pipelines because most of our computational science codes are what we call data parallel codes, right? So I'm operating on different pieces of a data domain on these architectures, and there's a lot of interaction between what happens on node 0 and what happens on node 1. So I'm constantly communicating, where I think a lot of these data parallel are more like there's someone from above that sends out a query or is looking for information and will combine it in certain ways, but there's not a lot of synchronization between all the resources at the bottom. What was the next question? Was there another question? No? Okay, yes.
So in your experience for vectorization, how about, for example, in C, using keywords like restrict and all, does it help much?
I think you almost have to use restrict. I'm going to defer to Todd because my background's primarily Fortran. I can do some C and C++, no.
If inlining works for you, you would not necessarily have to do restrict. And if it's a really, I'll talk about it this afternoon, but if it's a really simple thing for the compiler to analyze, you can probably get away without using restrict. There's some tests that it can do to make sure that there's not what they call aliasing between arrays.
Right, you have to be sure no one else, no other process is accessing that data that, yeah.
But yeah, I'll show some examples later.
Are there any other questions? Okay, we can take a break, get some coffee. We'll be back in 10 minutes. Welcome back to the second session of our introduction to Manycore. In this session, I'm going to go over the KNL hardware, which is the specific architecture we're going to work on today. So a little bit about the Xeon Phi. What we're going to use today is the second generation of Xeon Phi, and Intel made some design decisions when they produced this chip. I guess the biggest one is they based it on the x86 architecture, which means all of the Intel tools work on it. They didn't have to write a new compiler. They don't have different assembler. They could adapt their current libraries. And this helps us greatly too, because our users are used to running on Intel architectures. And so what they've done is they've taken some of their advanced x86 cores and in the first generation stripped out what they didn't need so they could add larger vector units, and then they've added some of those features back into KNL. And I'll get to that in a second. And this architecture and these cores support standard programming paradigms. So it's not like running on a GPU where maybe you need to write in CUDA or OpenCL. You can just use C, Fortran, C++. You can use MPI libraries, OpenMP. All of this works fine. This is one of the reasons we chose this architecture. We weren't looking forward to trying to teach 4,000 users how to use CUDA. They are specifically designed for floating point performance. So in that sense, it's not a general purpose chip like you would find in your laptop. One of the advantages of the Xeon Phi, and in this case, the KNL in particular, over the regular Xeon line is that it has high bandwidth memory. So it has a section of memory that is on the chip and optimized to provide data to the cores. This is the MC-DRAM, multi-channel DRAM. Also, it is a self-hosted system. On our first system, Stampede, the Xeon Phi was an add-on card, but it was still its own system. It wasn't just an accelerator. You could actually log into it, but it was quite difficult to manage because each compute node basically had two systems. It had the regular system, and then it had this card running a separate OS. We had to design a lot of tools to make that work. The KNL is much nicer in that it runs an OS just like the regular Xeon chips. So when you log in, it looks like any other Linux system. Okay, so a KNL, second generation Xeon Phi, can have up to 72 cores. The architecture you're going to run on today has 68 cores. And I mentioned this in passing in the previous session, but each core has its own L1 cache, but shares an L2 cache. Each core has 2 floating point vector units. Each core can run up to 4 hardware threads. So it's possible on our system to run 268 processes at the same time, because there's 4 hardware threads per physical core. Now, these cores are set up in tiles. There's 2 cores per tile. It's set up on a mesh. It's getting a lot more complicated quickly. I'll get into these details. Now, for most of this session, I'm telling you these things so you're aware of them. You don't have to be super aware of them when you're programming for this. You mainly have to be aware of the memory hierarchies. You don't have to worry too much about the mesh or where your process lands or where your task lands. We've done a lot of testing and experimentation, and although some benchmarks may show a preference for some cores, in general applications, we see no difference from where the processes run. The peak speed is, or the peak performance is 3 teraflops for double precision, 6 teraflops for single. And one of the important things is this high-speed memory, this MC-DRAM, gives you a stream performance of over 450 gigabytes. Stream is a commonly used memory bandwidth test, at least commonly used in the HPC industry, to see how quickly you can load data into the processor. Oh, and one feature I'm going to mention here, but I'm really not going to discuss in detail today or through this training, is this architecture is actually set up to run on OmniPath, which is Intel's networking technology. You can think of it as similar to InfiniBand if you're familiar with InfiniBand. I'm sorry, there's a question?
Is the L1 cache the 16 gigabytes?
No. That would be a great L1 cache. I don't know. Okay, so the question was, is the L1 cache 16 gigabytes? No. The 16 gigabyte MCD RAM can be used in either a direct mode where it's like regular DRAM or a cache mode where it acts as an L3 cache. Okay, so if you've had experience with the first generation Xeon Phi, that was the Knight's Corner. This is the Knight's Landing. This is just a quick look at the differences. So since this is self-hosted, it runs a full-blown Linux. If you actually logged into the Knight's Corner, you notice that Linux-wise, there doesn't seem to be much going on in that system or a lot of features available. That was because it ran a very stripped-down OS. The KNL nodes run full-blown Linux. Also, you can build a code for KNL that's binary compatible with all previous Xeon architectures. You could not do that for the previous generation. It was a very specific binary that only ran on that KNC. So the clock's a little bit faster. I've got access to a lot more memory because now, since I'm on a self-hosted node, I have access to regular DRAM. So as much DRAM as the 6 memory channels can support, which is about 400 gig. And I also have the 16 megabytes of high-speed memory that's local to the chip. It's a higher resolution chip process. I now have 2 floating point units rather than 1. And several of these features that they removed to make the first generation Xeon Phi, they put back into these cores. So now I have out of order execution. I have branch prediction. So it'll try to figure out which branch of the if-else statement I'm going to take. And now we talked about memory alignment a little bit earlier. Now I have fast unaligned memory access. It's not as fast as aligned memory access, but it's much better. On the previous architecture, you took a huge hit when you accessed unaligned memory. Now you take much less of one. But I can't quantify it. I don't know any numbers. Someone's asking. Okay, so here's a chip diagram. There are 36 possible tiles. Like I say, we have 68 cores, so we actually have 34 tiles. There's just a few things I want you to notice from this. The cores are laid out in a mesh, and the MCD RAM is local to the chip, connected to the mesh. And there are 2 memory controllers. So you have access to DRAM through 2 memory controllers. Each has access to 3 channels. And I just want you to remember the general picture here, because in a little bit, we're going to talk about quadrants and clustering and get a little more complex about how to divide this architecture.
What's a tile?
The question was, what's a tile? And I think it set me up for my next slide. I hope so. Yeah, a KNL tile. So a tile is composed of 2 compute cores. And this is your access to this mesh, right? So in this case, 2 cores share access to this mesh, and they share an L2 cache. So each core has these 2 floating point units in its own L1. So let's say you were running something on this KNL where you had 34 processes. You didn't have 68. For some reason, you can only run 34. you have some options here. Should you run spread out across these tiles, so you run one per tile to optimize your memory bandwidth to that core? Or do these processes do a lot of sharing, so you'd like to share an L2 cache?
So is this a hardware thing or is this software thing?
So what you're looking at is hardware, but the decisions you make, so the question was, is this a hardware thing or a software thing? The hardware is set up in such a way that you can make decisions as to where to place your processes to affect how they run. And so if what you need is a lot of memory bandwidth straight from MCD RAM or DRAM and not to share data with other cores, then ideally, if you could, you might want to run one process per tile. You think of how the hardware infrastructure is set up and how you want to optimize to run on that.
I'm beginning to understand. So we have tiles, which are physical things, and how's the communication between the tiles and the MC, whatever it was?
Okay, so the question was, or the statement was, we have tiles that are physical things. Yes. So to point that out, let me come back up here to the picture of the chip. Tile. I mean, you can see from the chip how it's laid out. And so the tiles, the processor, or the cores communicate on this 2D grid. And so there is a notion of cores being close to each other. And we've done quite a bit of testing to try to determine where exactly these things are running. And we haven't really seen a performance difference, say, if I run on this tile and this tile versus this tile and say this tile. Even though we know there are multiple hops and there's some latency there, but what we're doing is probably, those latencies aren't large enough to have an effect on the performance we see. In other words, there are much greater latencies and bandwidth issues here rather than this latency and bandwidth between tiles.
Now, that diagram, EBC is?
I'm not sure. This is a diagram I lifted from Intel. I know MCD RAM and DDR MC is the memory controller.
I think that's just the name for the memory controller.
For the MCD RAM?
MCD RAM. I forget what it stands for exactly, but it's the controller that, decides what goes in and out of MCD RAM. It's not something you really have to worry about.
So the other thing to pay attention here is that you have two different channels to memory. And later when I talk about NUMA nodes, that's going to come into play. So these three channels here go to DDR. These three channels here go to DDR. Or DDR, well, DDR, I mean DRAM. Just regular DRAM like in your laptop. These channels go to MCD RAM, which is on the chip. Okay, so this is a tile. So now we're going to go one level down. This is a core. I really want you to take note of only one thing. On this core, there are two vector units. Notice that one of these vector units has this little rectangle that says legacy. What's in that little legacy rectangle is a support for other vector operations, AVX, SSE, AVX2. So what you need to note from this is if you compile without using Mike AVX 512, let's say you compile with a lower level of vectorization, it will only ever use one vector unit on this core. It will not use the second vector unit. So half of the floating point performance is inaccessible to you. So it's important to at least build or try to build with Mike AVX 512. And this is just a picture of the instruction sets that are added to AVX 512. And then you see the legacy part. So everything in that red rectangle, that's only supported on one vector unit. And this is another comparison between the KNL and the KNC architecture. And whenever I say KNC, it's Knight's Corner, KNL is Knight's Landing. So they have the same length vector units, but there are two on the KNL. The KNL has more support for integer arithmetic. And I mentioned the alignment earlier, and it's got legacy support. And it has hardware division and square root on the chip, so on the KNC, it had to do that in software. So as I mentioned before, even though this is a specially designed chip for floating point performance, it looks like a regular operating system. When you log into the node, you don't have to learn a special language. You're not using CUDA or OpenCL. But this sort of ease or low bar of accessibility also hurts us, because a lot of people get on these nodes, oh, look, it's easy. I can compile my code just like on these other architectures, and I run, and the first thing they notice is, wow, my performance sucks. And so we try to set expectations and let them know, got to change your code. There's a question.
Does Intel provide the Linux?
No, we're running CentOS 7.5. So on our first system, we installed a KNL system last year, 500 nodes. It was an upgrade. And early on, we had a custom version of Linux from Intel because the kernel changes they needed hadn't made it into the main kernel branch. But now we're just running stock CentOS.
They have some kernel modules that load that give you access to high bandwidth memory and stuff like that.
Some of these other modules that work with Ziggy Linux?
Oh, for the kernel modules, they only work with the MCD RAM hardware, right? But it's the stock CentOS OS, right?
Mhm.
Yeah. Okay. Okay. So the point I was making earlier is just that people are disappointed with initial performance, especially if they compare to GPUs. And sometimes we remind them, well, you might have spent 3 months writing your GPU code for that architecture. You'll give us a chance and spend 3 months refactoring your code for this architecture. Then let us know how it worked. Okay, so now we're about to get into how this hardware works and tiles and quadrants, and don't pay a whole lot of attention. I mean, follow along, but in the long run, I'm going to talk about 2 different ways that these nodes can be configured. And this concept of quadrants and tags has to do with how it handles L2 and L2 caches. And in our experience, we've seen this doesn't make as big a difference as we expected in performance. So I'm going to explain this to you, but if you don't follow along or you don't understand, ask questions, but don't worry too much. Later, I'm going to talk about how we handle MCD RAM. That matters greatly. Okay, so each tile has an L2 cache that's shared. We saw this mesh. There's this concept of a quadrant. I'm going to show this to you on the next. I'm just trying to get you ready. Of a quadrant where this mesh is divided into 4. This is an artificial concept or an artificial construct. It's not in the hardware. It's in the software that drives the hardware. And depending on how the node is booted, these quadrants change the way the cores process cache misses. And so there's this concept of a tag directory, and that's sort of what tells the processors, the cores, where the data is or where the most recent real copy of data is. So if there's a cache miss, it tells the core where to get it. This is the memory mode stuff that I was talking about. This is what you will be concerned with. This cache miss stuff doesn't seem to make much of a difference in performance. I'm going to go deeper into these in a little bit. Where your data sits matters. So just remember, whenever you want to run, you probably want your data to reside in MCD RAM. There's one case I know of where that's not true, but usually you want to reside in MCD RAM. MCD RAM is the high bandwidth memory, but you need to be careful because there's only 16 gigabytes. And there are different ways to access it. You can access it as regular memory, which means you can specifically allocate to it, or you can use NUMA control to make sure by default your memory goes there, your data stored in memory goes there first and then spills over to DRAM. Or you can use it as a cache. So if you use it as a cache, it's basically just an L3 cache. Each tile has L2, each core has L1. This is an L3 cache shared among all of the cores. In our default queue normal, this is how it's configured. One of the main reasons it's configured this way is this is the easiest way for our users to use the system without changing their code. How your code uses cache is pretty much invisible to you. It's a black box. These are decisions made by the system. So what this does is it provides this large L3 for the data you're pulling from main memory to sit. And it can speed codes up quite a bit. I have one code using about 40 gigabytes on a node, and the difference between running in cache mode and say just DRAM is about 40%. Now this is a code that's very memory bandwidth dependent, but it makes a huge difference. This is the easiest way to use the KNL. Now, you can also run in what we call flat mode, and you'll see this reflected in the queue names that we use in the lab later. There's a queue called flat quadrant, and what that means is MCD RAM is configured as memory. So your code will not automatically use it because this comes back to this NUMA node concept. It looks like a different NUMA node, and the way the processor is configured, the default NUMA node, the default memory for the cores is the DRAM, not the MCD RAM. So to use the MCD RAM in flat mode, you have to do something. You either have to use a NUMA control command to tell the execution of your process to use MCD RAM first, or you use some of these tools within your program to actively allocate memory to MCD RAM. And just because it's not complicated enough, Intel gives us this option where we can do some in cache and some in flat mode, which, to be honest, we have not even tried. We have not had time to experiment with this. So these are the different ways you can configure the use of the MCD RAM. And this you should be aware of because when you run in the normal queue, you're running in cache mode. If you run in one of these other queues and it says flat, that's where MCD RAM is its own NUMA node, and to use it, you have to do something special. Now, cluster modes. This is where we can change the way an L2 cache miss is handled for a core. This is the one where I said, we don't see a whole lot of difference between the cluster modes in terms of performance. And some cluster modes are incredibly difficult to manage. And so, and bear with me on this because I'm not an expert on how the L2 cache misses work, but there is a tag directory in which, spread among the processors, a tag says where the L2 data resides or who owns this L2 data. And so if the core you're on needs some data, it's not in L2, it has to go seek out this tag. This tag tells it where to get the data it needs. Then it goes and gets that data from memory. Now remember, I've got this grid of cores. So it's possible it will walk this whole grid. All I'm going to say here is there's 3 modes. And the reason that's all I'm going to say is because I think the pictures are much better than the words. And so in the default mode Intel has, there's this all-to-all. And so this is pretty much, I think, how it boots up by default. And where if there's a cache miss, this tag it needs to find out where that memory is can be on any core. So it can go to any core on the mesh. Once it finds out where that is, that tells it where the memory is stored. So in this case, it's an MCD RAM, and you can see it has to go get the memory out of this MCD RAM chip down here, and then bring it back to the guy that initially asked. So there's a cache miss. It has to go it has to go read the tag, which is in this core. That core tells it where the data it needs is. It has to go to memory, get the data, and come back. And so here it's possible for it to walk this whole grid. I don't think we have any queues configured in this mode. This is the recommended mode that Intel has given us. And from what we've found, this seems to be the most performant, or by that I mean slightly better than the others, because I haven't seen much difference, and the easiest to use, in that this is a single NUMA node. We'll talk about NUMA nodes later because we have to worry about that with memory. But so in this case, what I'm guaranteed is that I might have to walk the whole grid to find this tag, but once I find the tag, the data is going to be close to the processor I found the tag at. So I get my cache miss, I come over here, oh, well, the data's right here. And so the idea is I'm minimizing the walking of this mesh for an L2 cache miss. Okay, there's this other mode called subnuma 4. So this brings it down even closer. So now I'm guaranteed that my tags and my data are all in the same quadrant. And so ideally, or theoretically, this should be the quickest. Everything's closest for cache misses. So I need some data. The tag's here, the data's here, I come back here, the fewest hops. But when you configure this, the way Linux sees this system, it looks like a 4-socket system. So now I'm running across 4 sockets. Remember we talked about affinity before? I really have to worry about where my tasks and my threads are placed. And so I can run this way, but it's much more difficult from a user perspective to configure my run to run correctly every time. And when we've run this way and compared the performance we see, say, in this cluster mode versus the other cluster mode, the quadrant, I don't see a difference in performance. And so we have one queue set up for this with, I think, only 56 nodes, only a handful of nodes. And it's primarily for testing because we don't expect most users to run this way. Although theoretically, it should give the best performance if you're thinking about L2 cache misses. We just don't see it in anything we run. And so that's why our default configuration is this cache mode with this quadrant configuration we put here. And Intel's even told us, don't do this. So Again, like I said, the differences in performance that we've seen, very minor, if any. So most of our nodes are in the quadrant mode. If you don't understand how this works, don't worry about it. This is where this system gets really complicated. I talked about the different ways you can do the MCD RAM, of which there's 5 different ways. I talked about this cluster mode, which you can do quad, or you can actually do halves. So you can do 2. So I think this comes out to like 30 different ways you can configure this system at boot time. And we've chosen, I think, 3 or 4 to represent in queues. And we have not tested many of these. There's just too many variations. We've chosen what we think will perform good and be easiest for our users to use. And I'm including all of this in this discussion mainly for the sake of completeness. When we first started doing this, we included it because we didn't know if it would make a difference. Now I think I'm safe in saying the different clustering modes don't matter. And so here's a really clear picture of that. So if you can read the graphics, everywhere what we're measuring is relative speed up. And so this sort of baseline here is flat mode using this all-to-all cluster mode. So flat cache mode. So by default, it doesn't go into MCD RAM. So it's going to DRAM. And everywhere you see the performance jump up, that's because we're using MCD RAM. We're either using it in flat mode where we use NUMA control to tell it to run out of MCD RAM, or we're using it in cache mode. And all of these benchmarks fit easily within 16 gig. So none of these are applications for this data set that say overflowed MCD RAM, were too big to fit. But you can clearly see for most of these, anytime you use MCD RAM, it's faster. There are a couple of exceptions. That's what I was mentioning earlier. For NAMD and MiniMD, these are both molecular dynamics codes. They do not depend on memory bandwidth. They have horrible memory access patterns, and the high-speed memory just doesn't affect them. It doesn't give them any advantage. Actually, I don't think you can tell it here, but I think is it NAMD? NAMD or maybe MiniMD. One of them can run slightly better with DRAM because the latency to DRAM is slightly lower than the latency to MCD RAM if it's running in flat mode. But for most codes we work with, memory bandwidth is an issue. And so that's why I'm harping on this MCD RAM and how you use it. If you run in the normal queue, it's sort of there by default because it's a cache. If you run in the flat queue, you need to do something to use it. And there are reasons you may want to run in the flat queue. You may have a code where, say, the code needs 40 gigabytes of memory and you're running on a single node, but there's one array you access over and over and over, and it's only 8 gigabytes in size. So you can actually run in flat mode where you specifically allocate that array to high-speed memory only. And everything else can go where it wants. You can put it in DRAM or you can allocate it in MCD RAM. And so you can optimize it. Now, if you run in cache mode, you might still get pretty good performance. But if you run in flat mode, it gives you direct control over where you want to allocate your data. Okay, so now we're going to talk a little bit about affinity and how the actual cores are numbered and where your tasks and threads land when you run on these. Are there any questions? Okay. Okay, so here's a picture. Ignore the quadrant part. Each of these little purple rectangles is a tile. And so by default, on this architecture, the cores are numbered across the physical cores. If you have experience with the previous K and C, it was exactly the opposite. The first physical core had logical cores 1, 2, 3, and 4. Here, we start at 0 and we go across the physical processor grid. And then for the next level, remember we have 4 hardware threads per core. So when you have hardware threads to the Linux OS, that looks like processors. It looks like, or cores. It looks like you have 288 cores on the KNL. If you cat proc CPU info, you'll see 288 cores. And so for this little example here, this is for a 64 core system. We have 68, but this is just for illustration. You see, when you get to 64, it wraps around. So you need to know this just in case you want to do specific core bindings. You need to know how the cores are numbered. And we have some tools that will show you actually where your threads run. And so this comes down to this LS topo view. You can see that this is one tile and there's core 0 and there's core 1. And then this shows the actual hardware threads and what the Linux operating system sees: 0, 68, 136, 204. And you need to remember, this is the same physical core. So if you were to do some sort of process binding or thread binding to 0 and 68, they would both be running on the same physical core. And this is why we care about affinity. So we discussed earlier a little bit about the Linux scheduler and how it tries to do load balancing. I have no idea what it thinks of when it sees a system like this with 288 logical cores and 68 physical cores. I don't think it has a clue, to be honest. So the tools we use have affinity baked in. If not, you may have to learn a little bit to assign affinity on your own. And this is one of the things we're going to teach you today. So I think today we're primarily going to talk about OpenMP, because by default, Intel MPI will give you the correct affinity for your core range. So if you run one MPI task per node, Intel MPI will say, okay, you can see all 288 cores. If you run 2 MPI tasks per node, Intel affinity or Intel's default settings are smart enough to say, oh, you task 0 will see 0 through 33, 68 through whatever, I guess 60 or 33 plus 68 is, and so on. It will give you the physical cores. It'll give you affinity there, so your threads can run in that range. It, by default, sort of does the right thing in equally subdividing the physical cores. And you can change this in Intel MPI with environment settings, or you can turn it off completely. OpenMP, what it does by default, which I'm going to show you in a second, is a little bit different. Because if we don't set anything, it does what Intel's runtime wants to do by default. And what we're going to show you is how to change this using OpenMP environment variables, maybe rather than Intel, just because the OpenMP environment variables work whether you're using Intel or GNU. And the one we're going to use is OMP proc bind. There's close spread, master. I don't think we're really going to say anything about master. And to be honest, I've never used it before. That comes into play when you're using OpenMP and you're spawning more threads from an OpenMP section. So you have nested OpenMP sections. So threads, cores, sockets. And here, what we mean by threads are the logical cores. So on the KNL, there's 288 logical cores. So 288 places a thread can go. When I say core, I always mean a physical core. If I don't put the word logical in front of it, I mean the physical core on the chip. Socket, I guess we'll talk a little bit about sockets, but on the KNL architecture, there's one socket. Although there are multiple NUMA nodes, which will come into play when we talk about memory affinity, because we're not just binding where a thread runs, where a thread of execution runs, what core it runs on. We're also telling the thread how to access memory. So right now we're just going to talk about binding and where it will run. And so if you don't set anything, this is the default. So you run 68 threads, it'll do one per core. When you run, say, twice as many, it will automatically wrap and run on the first hardware thread, or the 0 hardware thread and the 1 hardware thread. And this is an Intel runtime default. This behavior may be different if you're running with GNU. But the statement down here is, hey, if I'm running 136 or 204 threads, and if I have some sort of data sharing between threads, they're spread out on different cores. So they have a different L1 cache and they share an L2 cache. Maybe if I know I'm going to oversubscribe the physical cores, maybe I should change the way my threads are so 0 and 1 run on the same physical processor. Then they at least share the same L1 cache. And so you can do that with spread. And so what spread's doing is it's looking at the available logical cores of execution, and it's looking at the memory hierarchy, and it's trying to subdivide in such a way that threads close to each other, in like count, I guess, thread ID, are close to each other in the memory hierarchy. So now, when I'm running 2 threads per core, 0 and 1 are the same physical core. 2 and 3 on the same physical core. If I'm running 4, it stacks up this way. Where here, see, 0 and 1 are spread out across cores. And when I run, say I run 272 threads, it's aligned differently. So the other alignment you can do, and I'm not sure I've had a reason to do this one, but you might, is close, which basically means just pack the threads as closely as you can. And so in this case, let's say you were only running 4 threads, all 4 threads would be on the single core. Because you're looking at the logical cores and how they fit in the memory hierarchy, and you're filling it up as closely packed as possible. And this is just an overview. And you see when you get to 272 threads, they both lay out the same way. But ideally, you want to use spread. And in my benchmark testing, I have to say it's pretty much hard-coded into my scripts. Okay, are there any questions? Kind of flew through that, and it's 11:45, so I'm not sure we have time to start the lab. Okay. So we're supposed to come back at 1 from lunch. So we can break for lunch now. You have an extra 15 minutes and do the lab afterwards. Does that work? And when you come back, we'll get you started on the lab. We'll work on the lab for about an hour. Then we'll move on. Any questions? Okay, thank you.